time for our last lecture this morning. Our speaker is Pedersen from Aarhus, Denmark. He will give a talk about Cantor's type result due to formal Laurent. So you are welcome.
Yes. First off, I would like to thank the organizers for giving me the opportunity to give this talk. So we're going to talk about formal Laurent series F3. So let's start with F3, be the 3 elements. From that, we can construct the polynomial ring F3, so polynomial coefficients in F3. If we look at versions of such two polynomials, F2 and F3 of x, where g is non-zero, we have the rational functions noted F3 of x, which has the polynomials as a subset. Now, these polynomials sort of corresponds to the real number, the integers, while taking such versions is going to correspond to taking rational numbers. Now, we can actually give the polynomials over 3 natural value. So if we can take an f, we can get an absolute value by taking 3 to the degree of f is non-zero, and to if f is the zero polynomial. That absolute value we also have here by taking 3 to the degree of f minus the degree of g. Now, when we have the integers, the rationals, we also have the real numbers. How to get those? Well, normally we get them by completing the rationals with respect to our normal values. When we do complete the rational functions with respect to this absolute value, we get the formal Laurent series. So F3 of x inverse. So it's going to be sort of formal Laurent series where we have coefficients in F3. Now, this absolute value is ultra-metric. So, in particular, if we take two balls, they either intersect empty or one of the balls is contained in the other. That ability of being ultra-metric is contained both here and here. So our space here is ultra-metric, it's a field, it's locally compact, and hence it looks very much like the reals. But everything works in characteristic 3. So there's a difference, and the fact that it's ultrametric, it makes sort of doing geometry here rather hard. We have to do some other arguments instead. So, as I said, it's complete field, characteristic 3, locally compact, and we have the following absolute value. Now, in this world, we can do Diophantine approximation. Now the task is, when we do it here, well, we can also do it up here by translating what is approximation by rationals, by looking at approximation by elements of time. So that's what we're going to do. So first off, we're going to look at the unit ball. So let's denote that by L. So that is where we're restricted to go from 1 to infinity, and coefficients in F3, and if all the coefficients are 0, then it's a zero element. So that is going to correspond to taking the unit interval and the real line. You can see that if we took that one instead of x had 3 and just evaluated normally we just get the elements of the unit interval within base 3. Now, inside the unit interval, we have the Cantor set, which we made by saying we don't allow 1 to be in the base 3 strip. We can do the same in this world of forming the rank series, and then we get another sort of Cantor set. And what I have been looking at is approximation with respect to this Cantor set. Now, the space is locally compact, so the notion of after-all dimensioning still makes sense. And if we try to compute that for this Cantor set in the form of the Lorentz, we still get that it has a dimension log 2 over log 3, and if we take the gamma measure of the Cantor set, we get measure 1. Now, in 2008, Salt and Milani put the result in the real world about the approximation of elements in the Cantor set with respect to rationals of a certain form. So if we let psi be a function from positive reals to itself, then we can find the set V, K, psi as the elements in the Cantor set that are well approximatable by rationals of the specific form P03 to the n for infinite n's, where P is restricted to lie between 0 and 3 to the n. And what this showed was a type of function type result. So if f is a dimension function that has some sort of convergent, then we have the following result. So that is result in the real world. So let's look at what does that actually look like when going to the form of the ratios. That's what I've been doing. So first up, we restrict psi to only take powers of 3 as it's approximating the radius of both, and that only takes powers of 3. Then we look at the elements in the Cantor set that are approximable by, well approximable by nice elements, so elements of the form g over x to n, where g is restricted by degree n, and only have coefficients 0 and 2. And then what I have shown is that essentially the same result is true. So why is this interesting? Well, in the real case, the argument uses quite a lot of geometry to get the estimates. But we can't do that here. So instead, we have to use that we are in an algeometric space. So balls have non-empty overlap. So we have a really good control of the balls, and hence where in the real case we use geometry to get some estimates. You can count and simply keep track. So how do we prove that? Well, there's two parts. There's convergent part and divergent. So first off, we rewrite our sets as in terms of balls. So it's those elements Cantor sets that are infinitely many of these unions of balls. If we take the union and note by an, we see that it's the subs of the n times first we will learn that the fact that the series converge implies that if you take psi of 3 to n, that tends to 0 and tends to infinity. So if you take the c of psi, then I can get a cover by taking an, then taking the union over n is sufficiently large. Then I note that if n tends to infinity, the radius of the balls in the cover simply tend to 0 as I simply remove the largest of the balls. Now if we want to compute the f cover, f length of this cover, I simply get the sum and larger again. And then I have to count how many balls are there in this union. Well, that's a matter of counting how many elements are there in Fn. So the number of elements in Fn. And then I have to take f of the radius, so that's psi 3. Now this I can simply compute to the n. When I compute that, I get the sum from n larger than big N, and then I get 3, 2. 3, 2. The gamma f of psi of 3 to n, that tends to 0 as n tends to infinity by assumption, but this is always larger than the Hausdorff f of the DC of the psi set. So that's how you do the convergent. What about the divergent? Well, we need a bit more control of our impulses. So we are going to put a star restriction on our sets. So we only look at those balls where the center d over x to n are reduced fraction, and we can do that by imposing that g of 0 is 2. And still we can count how many elements there are on f star of n. When we have that, we're going to introduce the measure v by taking the gamma measure of Cantor set with the set I'm interested in. And then first off, we're going to show the result in the particular case where the approximate dimension function f is just gamma. So when we're computing the Hausdorff function. So how would we, when we have proved that, we can simply get the result for Hausdorff f measure by using Mass Transference. So how would we compute that? Well, I will give a sketch of how we get that. So first off, we reduce to the case where psi of 3 to n is more than or equal to 3 to the minus n. When we have that, the object is that our union is going to be disjoint, and hence the measure splits. Second law, we can look at what is the psi of a n star. How do we do that? Well, since it's disjoint, the measure splits, so it's simply counting the elements of f star times the radius of such ball. Now, normally, if it was in the real case if we took our stock gamma measure of the Cantor set intersected with some ball, it would be comparable to the radius of the ball to gamma. But because we have missing overlap in this world, we over here actually get that cost of F measure, cost of gamma measure of the Cantor set intersected with the ball is equal to the radius of the ball times gamma for all small enough and intersecting non-empty with the Cantor. So earlier I counted how many was disjoint union, and then we just have to take the measure of the ball, but that was just the radius of the ball, sine 3 to the n, and then took it out. And if I simply count this, I get 3 to the minus gamma, and then c of 3 to the n times 3 to the n to the gamma. So the next step is computing the sum from n equal 1 to infinity of the measure of a n star. Measure. But we have this, and we recognize this term as the one we have assumed to diverge. So this is simply infinity. This enables us to use the first part, or the divergent part, of Borel-Cantelli. So we have the sum diverges, so we need some control of how the mu of Am star and Am star So the fourth step, we simply compute mu of A n star times A n star under the assumption that the mu is larger than n. We can actually compute this. It turns out that it's 0 if 3 to the minus n is larger than or equal psi 3 to n. And how do we do that? Well, it turns out that if we take one of the balls in an star and one of the balls in an star, they intersect empty. So it's the union of a lot of empty sets. That's 0. And here we use that the d x to the n is reduced because we need the x. And it turns out that if we're not in this case, it simply splits mu n star times mu of n star. Else. And that is because we have enough control, we can simply compute what is this size exactly. I know when two balls intersect, and I know from here what this term is. Finally, when I have this, I have quasi independence. It's called. So under all circumstances, this is more than or equal to this. So if I want to use the divergent part of Borel-Cantelli, and simply substitute them there. So if I want to use it, I get, when I say mu of the c star of psi is larger than the sub of those I get from Borel-Cantelli. That's larger than the sub of another ones, which is 1. But we also have the restriction from above of 1, and then we have the result. Now, finally, we want to go from where our dimension function is just radius to the gamma to some general divergent function. And for that, we're going to need the Mass Transference principle. So if f is the dimension function, we have some defined transformation false, and then the Mass Transference principle says that we have sequence of balls, wedges tending to 0, and f dimension function satisfying the sum monotonic relationship, which is what we assume in this case. Then if any ball containing T satisfies some relation on the house of gamma measure, then for any ball we see, we can say something about the house of F measure. And that's exactly what we have here. So, by assumption, the sum of f of gamma 3 to n times 3 to n gamma diverges at to infinity. Furthermore, we can assume that psi of 3 to the n tends to 0 as n tends to infinity, as else our set W star C of psi simply be the entire concept. Now, if we introduce theta to be the function that takes radius and observe in f of the radius to 1 gamma, then we see this is theta of 3 to the n to the gamma. And if I then simply look at u of so the point is the sum where I have this function theta diverges. So the theorem, which is sketched over here, then take my of psi of theta, then that is defined as my of Cantor set. Now, if I take some ball inside the Cantor set, this still holds true. And then by applying the Mass Transference principle, I simply get the Hausdorff ratio of any ball times this set theta, any ball times this, where instead of theta at the psi, do c star psi would be equal to the house of f measure of the Cantor set when I intersect with the ball. So if you take the ball to be the whole thing, you get simply this, and that is the sum we wanted. Now, to final remarks, there's nothing special about 3 in this case. So, if we instead of starting out by having f3, instead took some other finite field, fq, where q is some prime to some power, and made the same theory, and instead of the Cantor set, made some general missing 50 set. So to stay constructed as Cantor set, we simply say some of the digits aren't allowed. Then we could take the entire theory and do it again. And that's how we make this. Thank you for your attention. Yes.